All right, let's go. Greetings, Earth and Space Explorers. I'm Bill Waller, an astronomer and science educator and communicator coming to you from Rockport, Massachusetts on a beautiful spring day in May 2020. For this month's Earth and Space Report, I thought I would share some insights regarding Earth as a planet with respect to the other two rocky planets that sport atmospheres and corresponding climates, namely Venus and Mars. To do this, I'm going to share my screen and show essentially a PowerPoint. Oops, there we go, okay. So we want you, all right. So the title of this presentation is called Comparing Planetary Climates and Why We Should Take Heed. This is my first Earth and Space Report, or really second one after the pilot Earth and Space Report, which I hope to post on on a YouTube channel dedicated to these Earth and Space reports. All right. So some of this you may know already, that the Earth has been warming on a global basis. Here are the measurements going back to 1880, which is a long time ago, 140 years ago, and going basically to, I think, around 2004 or so in this particular plotting. And you can see that the global Earth's annual average or mean temperature has been continuously rising. And the range is basically over 0.8 degrees Celsius. This year, it made it to a full degree Celsius rise over pre-industrial times. So a degree Celsius corresponds to about 1.8 degrees Fahrenheit. So we definitely have some global warming. And this is based on NASA's Goddard Institute for Space Science, Space Studies data. Okay. Question is, what's causing the warming? Is it natural or is it artificial? And the conclusion is basically that it is artificial, human-caused through the injection of greenhouse gases by combustion processes. And so I'm going to go to this graphic, what's really warming the world. And it starts off with the rise in average temperatures, and it's taken a while for the signal to get clear, but now it's very clear that there is something going on, that the Earth's land surface and ocean surfaces and atmospheres associated have been warming. And so that's the basic measurement, and the question is, what's producing it? So the first question is whether or not it's the Earth's orbit. The Earth has an orbit which is almost circular, it's slightly elliptical, and it can change in terms of the average distance from the sun a little bit, and it can change in terms of the tilt of the Earth as well, the degree of tilt, known as the obliquity. And this sort of change in orbit over long periods of time, thousands and thousands of years, does seem to have an effect associated with the ice ages, but over this 125-year span, it appears to be negligible. Okay. So what about the sun? Well, in previous decades, I thought maybe the sun might be partially responsible. It is a slightly variable star. However, over these time periods, again, the sun's fluctuation in brightness does not seem to explain the observed rise in temperatures. This is the modeled variation with 95% confidence being these dotted lines. And so we can't blame it on the sun. How about volcanoes? Whoops. Let's go back to volcanoes. Volcanoes. All right. There are reasons to believe that volcanoes will cool the Earth's temperature. because, well, first there's the dust that gets lofted up, but also there are these other chemicals, sulfate chemicals, that can uh, lead to cloud formation, and that will reduce the amount of solar irradiation on the Earth's surface. And so volcanoes are thought to cool. It's interesting which volcanoes these are. This one, I believe, is associated with Krakatoa in Indonesia, and this one is associated with Pinatubo in South America, I believe Chile. And so there was maybe a slight cooling effect, at least with Pinatubo, but it's hard to tell. Okay, but that certainly does not explain the warming. What about all three of these natural phenomena together? And the modeling suggests that none of these, even together, will produce the warming that has been observed. So if it's not nature, what about what people do to the land, namely deforest it, usually for farming purposes? And that turns out to have a slight cooling effect because trees their leaves are relatively dark compared to the cleared land. And so cleared land reflects more sunlight, and so the response of the Earth is that it gets a little bit cooler. That definitely does not explain the observed warming. How about our ozone pollution? Ozone is a type of greenhouse gas. It traps heat, and we used to add ozone into the atmosphere with our refrigerants. Various refrigerant chemicals would destroy the ozone in the stratosphere. And so we see here that maybe there was a little bit of warming, but within the uncertainties, it's negligible, and it certainly does not explain the observed warming. All right, what about aerosol pollution? Well, what's an aerosol? They are particles in the atmosphere, which can include very microscopic dust, but also molecules like sulfates. And they will cool because the sulfates are involved with cloud formation, and the clouds, again, obscure the sunlight. And so that can lead to some cooling. Again, that's not what's going on. This pollution seems to provide a cooling effect. And so there you go. It really is greenhouse gases. And I believe that this is based on the carbon dioxide mostly, but there are other greenhouse gases in the Earth's atmosphere, which include methane and water vapor, not in cloud form. And we do see a net warming effect, which does seem to explain the observed warming. And if you add all the human input, there's a beautiful fit or a compelling fit between the human factors, the human input through our pollution and our land use, and the observed warming. And then if you compare and contrast, here you have all the factors, both natural and artificial. And again, there's a fairly compelling case to be made that what we see here going on for the past 120, 140 years has been a global warming due to pollution by greenhouse gases, pollution of greenhouse gases into the atmosphere, most notably carbon dioxide, which has a long residence time in the atmosphere, around 100 years. Okay, I believe that's it. The rest is what this is all based on. It's based on NASA data and models generated from it. And then, of course, this was kindly put together by the Bloomberg folk. Okay, that's all I want to say about that. And so let's move on to the comparison. Now we've seen a little bit of what's going on Earth, what's going on in Venus and Mars. These are two planets that both have atmospheres to greater or lesser degree, and both of those atmospheres turn out to be dominated by carbon dioxide. hence the worth of comparing these planets and their greenhouse responses. Okay, so we have basically 3 experiments going on simultaneously. Going back to Earth, this is what is producing the greenhouse gas warming, or the warming by greenhouse gases, and it's places in the spectrum where the gases absorb light. In this case, it's infrared light that has been re-radiated by the Earth's surface. So the Earth's surface gets warm, it re-radiates in the infrared, it's heat radiation, and these gases absorb that light or that heat radiation at particular wavelengths. In the near infrared, for example, this is methane, and you can see it absorbing at around 2.4 microns and also 7.7 microns for methane. Ozone has an absorption above around 9.6 microns. And here's carbon dioxide, which absorbs at around 2.7 microns and 4.3 microns in the near infrared, but it has a whopping absorption in the mid-infrared at 15 microns. It really blocks the re-radiation of the Earth's surface from escaping the Earth. And so that stuff gets used to heat the Earth. Okay. Water is also an important greenhouse gas. Let us not forget. That's in water vapor form, not in cloud form, because clouds actually obscure the sun, and so they have a net cooling effect. Okay. Here's a comparison of the planets, basically with respect to the carbon dioxide, in the mid-infrared. And so here, Venus has this incredibly strong absorption at 15 microns, as does Earth. But Earth also has these other absorptions of ozone and water in the mid-infrared. And then Mars has a surprisingly strong absorption at 15 microns due to the carbon dioxide in its atmosphere. The atmosphere of Mars is incredibly tenuous, very thin, but it's almost all carbon dioxide. So it ends up having a net greenhouse gas warming effect. So let's look at Venus first. What you're seeing are the cloud tops made of sulfuric acid. Oh, the joy. So the sun, a lot of the sun does get blocked, but some of it makes it through to the surface and warms the surface. And once it gets re-radiated, the CO2 just completely traps that infrared radiation, which causes Venus to be the hottest planet surface in the solar system. So here's some basic info. It's about the same size as Earth, so it has a similar surface gravity. If you were on the bottom or on the surface of Venus and you dropped something, it would fall at the same rate. The big difference is it has a huge amount of atmosphere. It basically has 93 times more atmosphere. The pressure is 93 times greater than the Earth's pressure at the surface. It would be like being at the bottom of the Earth's ocean. The pressure is so great. It's enough to crush a car if you had the windows closed and the doors closed. And almost all of this atmosphere is comprised of carbon dioxide, 98%. Now, in the absence of an atmosphere, Venus would be warm. It's closer to the sun than the Earth, and so it would get warmer. It would be around 80 degrees to 100 degrees Fahrenheit. But instead, because of this atmosphere, its surface temperature is 890 degrees Fahrenheit. So tremendous greenhouse effect, hot enough to melt lead on the surface and vaporize sulfur. Yikes. Earth is a far more modest affair. The greenhouse gases are basically trace amounts. Most of the Earth's atmosphere is 78% diatomic nitrogen, followed by 21% diatomic oxygen. And then you have the trace amounts of carbon dioxide, CO2, methane, CH4, nitrous oxide, nitrogen oxide, N2O, and H2O, or water vapor. Okay, so those are the trace gases, but those are the ones that produce the greenhouse warming. And for Earth, these gases combined produce a 14% effect as measured from 254 Kelvin in the absence of an atmosphere to 289 Kelvin with this atmosphere. So that has been enough to keep Earth's oceans in liquid form rather than frozen over for most of Earth's history, which is a 4.6 billion year old history. So that's the story with Earth. Mars is a little more intriguing. It's half the size of Earth, and so it's approximately an eighth the mass. And as a result, its surface gravity, the acceleration of gravity at the surface, is almost a third that of Earth. Its surface pressure, the atmosphere, there isn't much there. It's 1/157th that of Earth. Very thin atmosphere, but what little atmosphere it has is 97% carbon dioxide by mass. And so that's 27 times more carbon dioxide overlying this surface, overlying each square meter of its surface than we have on Earth. And that produces a scant 4% warming as measured compared to what it would have without an atmosphere. Okay. So here's a little bit of technical stuff. You can just take a break for this, but basically, it seems that this CO2 does make a difference. How much CO2 per unit area overlying each square meter is a worthwhile thing to measure. And so you can derive this pretty simply. It's the mass per unit area is equal to the surface pressure, which can be measured by us here on the ground of Earth, but also with spacecraft that have visited both Venus and Mars. You can measure the pressure, and you divide that by the acceleration of gravity, and that has been measured as well by using spacecraft. And then there's this multiplier, this F, which is the fraction of the atmosphere, which is comprised of CO2, the fraction by mass. And if you work this out using data from NASA, you get Venus having 1 million kilograms overlying every square meter. No wonder it's crushing. And Earth, far more modest, 6 kilograms per meter squared. And then Mars intermediate would be 167 kilograms per meter squared. So that's 27 times more than what Earth has, despite the thinness of its atmosphere. So this greenhouse gas will modify how warm the planet gets. First, you have the sun. You start with the sun. The sun produces a flux at the distance of the planet, and that is equal to the luminosity of the sun. That would be in watts, for example, and it's a lot of watts. And then you divide by this dilution factor, which happens to be the area of a shell at the distance of the planet, 4 pi d squared. And that'll give you the watts per square meter that is irradiating the planet. Now the planet will respond. Some of that radiation will get reflected according to the reflectivity, which is called the albedo. And so you take that F solar and you multiply by 1 minus the reflectivity. You want the amount that's absorbed by the planetary surface. And once absorbed, the planet will heat up to some temperature, which is simply equal to this constant times the temperature to the 4th power. So one can actually solve for the temperature based on what the sun is doing at the planet and how the planet is reflecting or not reflecting the sun's light. Okay, so this is basic physics that can be taught in high school. All right. So the result is that without an atmosphere, Venus would be fairly clement. Would be around room temperature, a little warmer than room temperature, maybe up as high as around 100 degrees on average Fahrenheit. Um, Not awful. You'd have to wear a spacesuit because there'd be no atmosphere. But that's what is predicted based on the estimates for the reflectivity of the material making up the surface of Venus. And but in truth, the temperature is much, much higher. It's 450 degrees Celsius higher, or 810 degrees Fahrenheit higher. It's a lot higher. And so the percentile warming in kelvins is 150%. Okay, so Venus is definitely the poster child for global warming. Earth is a more modest affair. Its temperature would be below freezing, minus 19 degrees Celsius or minus 2.2 degrees Fahrenheit on average. But the temperature causes it to be a little bit greater than that. So on average, it's just barely above freezing. And the amount that one would get is around 13.8%. Okay. So that's Earth, about a 14% effect. And that's what's kept Earth from freezing over for most of its lifetime. Mars, right, this is 35 degrees Celsius. So this is above freezing, yeah. Oh, sorry. Mars is without an atmosphere, it's very cold on average. And with its atmosphere, we see basically an increase in temperature, which is still below freezing, I believe. But that leads to about a 4% warming that we see, okay? And you can plot all this where you have the warming, the change in temperature with respect to what you'd get without an atmosphere, with respect to the amount of CO2 overlying each square meter of surface, okay? And so let's begin with Earth. Earth is a 14% effect. It's the warming is around 14%. And you see that is due to carbon dioxide, but also the water vapor and the methane and maybe the nitrogen oxide as well. Those are the other greenhouse gases. And it turns out that the CO2 is only about a 40% effect of this overall. And so that brings down the warming to about 6%. Okay, so that's CO2 only. Now Mars has only a 4% warming as estimated, but you have to remember that Mars is a fairly dusty atmosphere, and so that is obscuring the sunlight, and so the surface is not getting irradiated as much as it would otherwise. And so if you took out that dust effect and just considered the CO2 by itself, it would get up to just short of 10%, maybe 9% warming. All right. Then there's Venus. Okay. If you considered the reflectivity of Venus's cloud tops, you would get a very high amount of warming, about 200%. But if you consider just the reflectivity of the surface itself, to determine how warm Venus would be without an atmosphere, then you end up getting a lower 150%. And there does seem to be a relationship. I wish I had more planets with carbon dioxide atmospheres, with atmospheres containing carbon dioxide, but alas, I don't have any that I know of in the solar system, certainly. There is Titan, which has a significant atmosphere. It's nitrogenic atmosphere, and maybe some of those nitrogen molecules have greenhouse effects. But here I wanted to just focus on the CO2 and see whether we could get a relationship. And there does seem to be a relationship whose fit in this log, this is powers of 10 here versus powers of 10 here. And you end up getting a power law where the the warming goes as the amount of CO2 to the 0.28 power. And so that's basically the effect that I found. There seems to be, yes, it's CO2 which drives warming. And so here are the conclusions, that there's CO2 concentrations in all 3 planets, and they are responsible for warming all 3 planets. It doesn't go the other way around. Greater temperature produces greater amounts of CO2. It's basically one where the CO2 concentration is driving the warming. I believe this planetary comparison puts the kibosh on the reverse thinking. Okay, Venus is the poster child for this sort of warming. It's 150% warmer than it would be without its thick atmosphere of carbon dioxide. Yikes indeed. Martian surface is warming less. It's like 4% instead of around 10%, based on the fit. And that is probably due to the atmospheric dust, which blocks incoming sunlight. And then finally, the Earth's surface is warming more due to other greenhouse gases in its atmosphere. The overall warming is around 14%, and the CO2 is only contributing about 6% of that or so. I can't remember. 40% of 14, I think, yes, 6%. And that is all due to the injection of anthropogenic pollution into our atmosphere, with the Earth's CO2 content having been cranked up by a whopping 44%. All right, so those conclusions lead to what I'm jokingly call Waller's law of planetary warming. I wish I had more planets, but it looks like it's a power law with respect to the amount of carbon dioxide overlying every square meter on each planet. And if you looked at just the last 150 years, the amount of warming, that 1 degree Celsius warming, that leads to a percentile warming over what was there before of 0.35%. And that is consistent with this relationship. If you up the CO2 by this amount, you would get warming that would exceed what we had by about 0.35 to 0.5%. So this seems to be consistent with what's been going on over the past 140 years. So bottom line, we have to take heed. We have to recognize that global warming by greenhouse gases is an interplanetary affair. It's something not unique to Earth. It's shared, and the relations suggest that the more CO2, the more warming. And so if we are to keep our warming below 1.5 to 2 degrees Celsius, then we're going to have to really double down on reducing our atmospheric CO2 content. And you can do it 2 ways. You can reduce the emissions. So that means not burning fossil fuels for most of our industries and our transportation. So that's decarbonizing our industrial processes and transportation processes, and our household warming processes. We have to decarbonize that. And we can also increase our CO2 uptake. And there's 2 ways to do that as well. You can do it organically with trees. Trees take up carbon dioxide as part of their photosynthetic ways, and they make wood out of it. Okay, they turn the carbon into wood, cellulose. And so that's one way to draw down the carbon dioxide. Also, we have to stop clear-cutting forests because that leads to a direct carbon loss, either through burning or just the fact that you don't have those trees doing photosynthesis. Okay, so that's the natural, organic way to do it. There's also using kelp is another way to, kelp beds to absorb carbon dioxide. And then finally, there's artificial ways of sucking up the carbon dioxide and sequestering it or doing something else with it. But I'd have to say that that's pretty much well into the future, and our issue is becoming more and more drastic, and so we're probably going to have to rely on the decarbonizing of our industry and transportation and energy use, energy production and use. We're probably going to have to go that way, along with reforesting the tropics, things like that. And so I hope that this was of interest to you. Next month, I'll be doing another Earth and Space report, and that will probably involve a student, a high school student here in Rockport High School, who's been working on a biodigester in the greenhouse at the school. And I'll interview her, and then she'll show some slides describing what this very earth-based system does, and what it can be used for, biodigester. Okay, and then probably June 21st, I'll do another Earth and Space report that has to do with what's going on Earth and on space during the solstice, the winter solstice in the northern hemisphere, and the southern, and the summer solstice in the northern hemisphere, and the winter solstice in the southern hemisphere. Okay, so that's it for now. Thank you so much. Bye.